Okay, so welcome to Mechanical Engineering Systems. I have been teaching this class for, I don't know, last 10 years. And I personally enjoy this class because in this class, you get to uh, think of systems. So for example, you have studied engineering design, you have studied mechanics of material, you have studied maybe design of shafts. In this class, we will combine all that knowledge, and at the end of the class, I will teach you how to design an internal combustion engine, a single cylinder internal combustion engine. So that is the mechanical system we are targeting for. But before we get there, we need to understand how to design the connecting rod. We need to know how to design the shafts. We need to know how to design the gears and how to design the springs, all that stuff. So we will pick up all this knowledge and finally we would apply this to design an internal combustion engine. And it's a very fascinating subject. I have been studying this for a very long time, and I enjoy teaching design. My hope is that you would be able to apply some of this knowledge when you go to industry, because they will ask you like, hey, can you design a cylinder? Can you design a pressure vessel? How would you apply forces? How would you use the software to analyze? So all those questions we will try to answer in this class. Now what I'm going to do is I'm going to quickly go through the syllabus and then answer any questions that you may have related to syllabus. So bear with me, because now what I need to do is I need to share my screen. So okay. So online students, can you see my screen? Okay. Now, in this class, we are going to look at how to design the complex mechanical systems. And here is a brief overview. My name is Sangram Redkar, and my office is in Technology Center in 101. Course description, we are going to talk about design and modeling of multi-component electromechanical systems, computers, controllers, electronics, hardware, software development, and so on. So this would be a step further from the design class that you took, EGR445. I believe that was with Dr. Nam. So, and EGR343, which is mechanics of material. And so this will be the advanced course. And I would be very honest, this will be very practical. So whatever material that you learn in this class, it's going to be directly applicable to industry. And you will find yourself that the material that we study here is indeed applicable to the mechanical engineering profession. So this is the textbook. And again, any edition of this textbook is fine. If you want a paper book, it's available on Amazon or eBay, so you can buy that. If you find an older edition of the textbook, that's totally fine. The students told me multiple times that they did not refer the textbook, they did not have to use the textbook. That's fine, but I would strongly recommend that to get hold of a copy of this textbook, so that if you have any questions or if you need some additional information, most importantly, sometimes what's going to happen is you are going to use the data from the data book or engineer's handbook. So those tables are available in the textbook. So that is very helpful. So if you have a textbook or a soft copy of the textbook, then I would say, okay, look at this table. And then from this table, you have these 10 different materials, we are going to choose material X. So what is the strength of that material? What is the Poisson's ratio? What is the factor of safety, and so on. So at that time, it would be useful to have the soft copy of textbook. Hard copy you can buy from Amazon. Again, attend all the lessons, and I don't know how COVID is gonna play out in the next few weeks. So just be prepared that if I get in contact or if I have to quarantine, I would be teaching 1 or 2 classes via Zoom. But the classes, I'm hoping that classes, I don't plan on canceling any classes. And in a rare event that the class gets cancelled, I would refer to you to the online video that you should take a look at just to refresh yourself and keep yourself updated. And then when I come back, I will cover the material. So again, look at your grades. Make sure the grades are correct. 90 and above, A's, B's. Most of my students, based on my past experience, they get A's. Very few get B's, never had C's. And it's very difficult. You have to work really, really hard to get a D. So that means don't submit anything, don't do anything. Yeah, so again, drop, add, class, withdrawals, syllabus. This is the schedule. So it goes by weeks. And what has happened in the past is, depending upon how fast or slow I go, I may be able to cover some material in 1 class. I may be able to cover some material in 2 classes. So this is just a tentative syllabus. So this is the guideline that I want to follow. And again, I have assigned kind of homeworks, and I have assigned some preliminary dates for homeworks. But if you are not able to cover the material by that time, I would certainly extend it. And then if you have any personal valid university excuse or a reason, for some reason you are not able to finish it, that's okay. You won't be penalized. So just try to do your best, but try to finish all the quizzes and all the homeworks before 2 days before the final grades are due, so that we can effectively grade and post the grades. And I tell you the real problem behind that. If you don't turn in your work, I cannot post the grades for all the students if someone, 1 or 2 students' grade is not uploaded. So which means, and I think most of you are graduating. I don't want to prevent you from graduating. So please try to complete the work. Give me 2 or 3 days to finish grading whatever is pending from your side. Also, again, if you need extensions, that is totally fine. You won't be penalized, but try to understand the material and try to work through the problems on your own. And once you start working through the problems, I'm pretty sure you will enjoy it. That's what students tell me, that hey, it's like solving a puzzle, and then finally making the part, building the part. That's fantastic. So as you can see, we are going to talk about design of quarter joint, knuckle joint, shaft and piece, turnbuckle, screw jack, springs, spur gears. And believe you me that I usually cover a lot material. So in a couple of times I actually finished the entire book, 900-page book. The entire book I finished. Bevel gears, worm gears, then internal combustion engine, design of internal combustion engine. And then in the past, I was able to cover these additional topics. It seems like, oh wow, there's a lot of material. But the idea is, once you have a fundamental understanding of how you design a spur gear, that knowledge can easily be translated to the helical gear, worm gear, bevel gear, and to be honest with you, to a lot of power transmission machinery. So you'll understand. Once I'm done with 1 or 2 designs, like design of quarter joint, design of knuckle joint, design of screw jack, you'll get a feel for designing some random object. Say, how do you design this bottle? And then the same design principle. So this is like a pressure vessel. The only thing is there is no pressure inside, but you will check for hoop stresses, transverse stresses, the failure, then you'll see for the internal pressure limits and all that stuff. Or how would you design this lever? Once you know what is the finger force that an average human can press, is about anywhere between 10 to 50 newtons, then you can actually design the lever arm and all that stuff. So that will be discussed in this class. And now again, classroom behavior. Please go through this. Plagiarism. So please don't cheat or don't copy solution manuals. If you want to work with someone together on some design problems, that's okay. But I want you to turn in your own work. Just don't tell me, hey, I work with him, so whatever grade he got, I should get the same grade. That doesn't work. Actually, I have had students telling me that. So if you want to form groups, Discord, whatever, everything is fine. And if you don't understand any material, just stop by my office. My office door is always open. I'm always here. Or shoot me an email, or send me email. My suggestion to you would be not to use the email from Canvas, because sometimes it doesn't get delivered and then students feel, hey, professor is not responding. Just use my issue email, because that comes directly to me. So rather than routing through Canvas, just use my email and I will reply immediately. Another thing, if you have any concerns, you need special accommodations, let me know. But everything is take home, so I don't think you will have any issues. All the exams, homeworks, open notes, open book, open internet, so that's totally fine. Now, one thing I want to tell you, and this is very important, is some of these quizzes and homeworks will require, they're easy, but will require some sincere effort. What do I mean by that? Is the idea is you design some basic dimensions. So if you want to come up or say design a shaft, what is the most important thing? You need to know the diameter, you need to know the material, but you realize that once you go through this course, that you need to specify the tolerances, geometric allowances, and etc. etc. So you will have to do some CAD modeling. And I'm assuming that everyone is familiar with one or the other CAD software, like SolidWorks. The other one thing with SolidWorks is great. Sometimes the student have had issues downloading the SolidWorks, or if you have Mac, SolidWorks does not work. So there is Autodesk software that is free for students. You are welcome to use that. It is equally friendly, and there is portability, so you can go from Autodesk, Inventor, or Fusion 360. I know for a fact Fusion 360 is free. You can use that, or if you want to do SolidWorks, SolidWorks is fine. Any questions? Anyone who has not done SolidWorks at all, this is the time to tell me. So when I say not done, that means that you have taken the class, but you are not comfortable. That is also okay. Just tell me now. Just one student, everyone else is comfortable? Because I'll tell you, no one does designs by hand. If you go to industry and if you tell them, hey, I know I'm a mechanical engineer, I know design. I can design, but on paper, not in CAD. They'll say, sorry, but we just use CAD. So gone those days when you used to sketch and present, oh, this is the sketch, and there will be someone who will CAD it for you. Now, where we are going is there is a design problem. You would identify what are the most critical dimensions or what is the most critical function, and then find out those dimensions, do a rough sketch, and then migrate to the CAD. then what you do is you construct the whole model and then perform something called as finite element analysis, which is actually meshing the system. And this is actually simple: meshing the system, applying the boundary conditions, applying the loads, and running force and stress type of analysis. It's not difficult at all, but the idea is for that you need a baseline model. And I will actually go through the materials, that way you will understand. Let me go through the quizzes and homework. So I just want to make sure that you understand the amount of work that is involved in completing some of those. And if you think that is unreasonable at this time, please let me know. Any question on the syllabus? Everyone okay? Okay. Online students, any questions on the syllabus? Okay, now I am gonna go to my issue. Bear with me for a second, and I will go through. I thought I had my issue open somewhere. Okay, it's gonna take some time for me to go back and forth, but if you have your computers, I would strongly encourage you to go to my issue, go to the course shell, and here are the homeworks and quizzes. Let me share my screen for my online students. Okay, you should be able to see everything now. So these are all the homeworks and quizzes. So if you look at this homeworks, there are 5 homeworks and 5 quizzes. So I would actually quickly talk about what is in the homework. And even the homework says SP20, they are the same homework. So I would follow the same homework. So first homework, homeworks are easy. Quizzes require significant amount of work. And please understand, I have given you some answers, but these answers, some of them are not correct. And the reason for that is when someone calculated those answers, the assumptions that person made could be different than the assumptions that they are making. So if your answers don't match with the answers that are given there, that's totally fine. And actually, in a lot of cases, you will observe that your answers won't be different. One request: whenever you upload, don't upload the pictures. If you want to take pictures or if you want to do scanning, just upload that as one single PDF file. Scanning is free all across the issue. If you have a phone, there are very nice scanning apps. So it would be easier if you scan, take photos, crop, and make it one single PDF and upload that as the submission. That would help us a lot. It's very difficult to grade when there are 10 different pictures that one has to go through. So scan one document per homework per quiz. As you can see, homeworks are just calculations. But if you go to quizzes is significant amount of work. So, and this is again, so even though it says work alone, there are some parts of this assignment that you are expected to work alone. So see, we are asking you to design a quarter joint. I will explain design of quarter joint. I will work out a design of quarter joint from start to end in this class. So I will find out all the dimensions. I will actually draw a nice sketch and I will actually show you how to design a quarter joint in this class. So that is the first step. So which would be 2 points. Neat sketch. Just draw a handwritten sketch. And then next part is create a solid model of quarter joint using SolidWorks. Any CAD software is fine. You will have to create a CAD model. If you are not comfortable with CAD, you should let me know now. Then create an engineering drawing of quarter joint. Now, what is engineering drawing? If you go online, there are some resources on how to create engineering drawing. So basically from SolidWorks, you can create an engineering drawing, and that engineering drawing is sent to the production facility to create that quarter joint, to machine that quarter joint. And then here are basically some hints, some YouTube videos where they show you step by step how to create a quarter joint in SolidWorks. Next thing, I want you to assign GD and T. Unfortunately, you haven't been exposed to geometric tolerances and designing. But trust me, that is super duper important when you go to industry. They will ask you, if you want to be a design engineer, do you know GD and T? So for that, there are some resources on how to assign GD and T. It's super simple. And then how to create an engineering drawing with GD and T in SolidWorks. So step number 4 is going to take some serious effort. Okay, so please understand. Then the next part is perform finite element analysis. You may say, what is this finite element analysis? Software will do that for you. It's just clicking few buttons, adding some information, and then the analysis will be done. The software will find the stresses and displacement and deformation, all those for you. For that, there is a YouTube video, but it does with ANSYS. There is another YouTube video. You can just Google quarter joint FEA with SolidWorks. It will show you the quarter joint FEA with SolidWorks. Then the animations are super cool. The SolidWorks will actually perform the animation, and you can save that animation. And you can see the last part is 3D printing. Everyone comfortable with 3D printing? Anyone who does not have any experience with 3D printing? Okay, so if you don't have any experience, I would actually encourage you. I will actually connect you with my grader and TA who can help you on 3D printing. But how many of you have a personal 3D printer? Okay, wow, most of you. So that's fantastic. This would be a good time to start your own business. So you can basically 3D print the parts for your friends and recover the cost of your 3D printer. Yeah, so 3D printer, a scale joint, and then you can actually print your name on it, take a picture, and upload. The reason for that is once you have that quarter joint in your hand, and once you see, it makes a lot of difference. Like, hey, this is the dimension, this is the point. If I pull this quarter joint, I would see that I see some sort of cracking appearing on this particular part, all that stuff. So that's why. But again, if you are not comfortable in 3D printing, that's okay. Once you have the solid model, 3D printing is easy. That's why there is just 1 point for the 3D printing. So what I'm trying to say here is quizzes are significant amount of work compared to homeworks. Okay, does anyone think that this is unreasonable, or can you do it, not do it? Okay, homework 2, same stuff. And to be honest with you, if you watch the video lectures, I have actually worked out some of these problems in the video lectures. So you would see, again, same thing here. It's a design of double quarter joint, then design of knuckle joint. Homeworks, as I told you, are not intense. They are simple. The quizzes, unfortunately, they are going to take significant amount of time. But sooner you start, better it is. So this is the screw jack. And again, you have a toggle jack. I don't know if you know what toggle jack is. That is the same jack that is in your car that comes with that the manufacturer gives you. So if you need to change the tire for some reason, that is the toggle jack you use, and then actually lift the car. That is the same thing. So homeworks are easy, quizzes are intense. So don't wait till the last minute. And please note that they are assigned differently. So just to give you the grading criteria, quizzes will be 60% of your grade, homeworks would be 40% of your grade. There's no grade for attendance, so but everything should be uploaded online. And there are just 5 quizzes and 5 homeworks. And as you can see, to be honest with you, homework 1 is January 25th, quiz 1 is February 8th. So the expectation here is that you don't wait till you finish homework 1 to start for quiz 1. Finish homework 1 as soon as you can and move on to quiz 1. That is the expectation. Otherwise, I promise you, you will fall behind. Say you say, hey, I'm going to finish quiz 1. I'm going to finish homework 1. I'm going to wait till Jan 24th and finish homework. It will take you 1 day to finish homework 1. And then I'm going to wait. And I'll try to finish quiz 1 from Jan 26th to Feb 7th. But it's not going to happen. Quizzes will take anywhere between 2 to 3 weeks, and you will have to do those in steps. So you finish first part, second part, third part, create CAD over the weekend, do that part, and then 3D printing would take maybe 3-4 days. So everyone understood this? Okay. Okay, any questions from my online students? I don't see any questions from my online students. So what I'm going to do now is I'm going to start. Yes. Oh, you can use a simple paper, and your scanner would add that engineering paper background for you. So, or actually, I will be honest. If you are going to use iPad or some other note-taking device, you say, hey, I want to just use my note-taking device, that will very nicely create an engineering paper background for you. So it doesn't matter. I say engineering paper because that is typically the convention that you do design on engineering paper. And there is a strong reason for that. The reason for that is, if you look at engineering paper, it has basically lines. So when you are trying to sketch something, that is a good reference. So you can create nice proportional sketches because you have the line references. But if you want to use the regular paper and then add lines, that's totally fine, because you will have to dimension the sketches. So engineering paper helps, but you don't have to go all the way and pay for engineering paper. If you have an iPad or something, you can just use an engineering paper. There was another question. For 2 minutes. Any questions? Yeah.
So if we use the renovation of the 3D print, do we have like a budget there?
Oh, just blame it on me. So basically, you've shown that this is for EGR445, and you should be okay. But I would strongly recommend that try to use some other 3D printer, because those 3D printers, well, they are used a lot. So, and you have so many friends who will be able to help you, right, in this class for a small fee. Okay. And actually, I have 4 3D printers set up. We had the same issue because the students in the innovation hub, the students were using the 3D printers in the innovation hub, but they are breaking down. So what I did for the class, I just ordered 4 3D printers. And I don't think it is really necessary, but if you think that you need access to those 3D printers, I can make those available. Or even better, if you wanna take one home and then just return it at the end of the semester, that's fine too. But then you have to help other students in 3D printing. Oh, that's totally cool. So those 4 3D printers I bought just for class use. Okay, any other questions, concerns, ideas, doubts?
How big is it's like I have my own at home, but I don't have the biggest 3D printer.
Oh, then you can scale down the part. That's totally fine. I just 1 by 2 because I know that that dimension would fit the 3D printers that we have. But if your 3D printer is super duper small, you can do 1 by 4, 1 by 3. That's totally fine. Yeah. And then use it that as a keychain. Yeah, look, this is a 3D printer. Or give it to your friend. Hey, look, I got you a gift. Valentine's Day gift. What is this? A quarter joint. Oh, actually, there is a funny story behind it. Okay, don't mind my jokes, but I tell you a funny story behind quarter joint. One of my students really did that because that is the perfect time. If you see quiz number, so quiz 1, you turn it in by February 8. So he already had the 3D printed model, right? So what is the purpose of quarter joint? The purpose of quarter joint to put 2 pieces together. So he said, look, this is my gift to you because this is the joint, quarter joint, joins 2 different things. So something like that. Cheesy, that's okay. Anyway, I said, man, you're cheap, but that's okay. But then he said, oh, I did design myself. I put my blood and sweat and all that stuff in it. So yeah, worked for him. So quarter joint, oh yeah, quarter joint, if you want to 3D print and use that as a Valentine's gift, that's fantastic. Just don't gift me, you can gift anyone else. I have a lot of quarter joints at home. So, okay. Anything else? Any other questions? Okay, I'm gonna now start sharing my iPad. Any comments? Okay, so okay. Okay, and I'm going to periodically ask for my online students if they have any questions or if they see the material, because believe it or not, I'm overloading Zoom. Basically, I'm doing streaming, then recording. At the same time, I'm going to use my iPad as a whiteboard. So many a times Zoom crashes. So, and we may not notice it, but online students, they don't see, or it will come in like short bursts, and that is very annoying. So yes, front light, yes. Main light. Now how would I write? No, I can. There is a little screen. Okay, don't fall asleep, okay? Other than that, I'm okay with it. Oh, and by the way, these slides are already posted on Canvas. So you don't have to copy anything down. And what I'm gonna do is I'm gonna write everything on the slides. I will save those slides and upload that on Canvas. So okay. Any questions? So in today's class, what I'm gonna do is I'm gonna start from the very beginning. And very beginning means remember mechanics of material from there. So first question is, what is stress? What is stress? Correct. So which is load divided by area. Now comes the tricky question. How many types of stresses do you know? Many. Okay. Yeah, tell me. I'm all ears. There are two types of stresses. Only two. The first type of stress is normal stress. And second type of stress is shear stress. And please remember this, okay? Because unfortunately, this fact is not stressed as it should be. You'll get my jokes, don't worry. Or I can raise my hand so that you know that I cracked the jokes. So normal means perpendicular. So please understand, why do we call stress a normal stress? Normal stress load is perpendicular to area. And when you have load that is perpendicular to area, so I'm gonna show you. So this is a rod or a bar. And there is a difference between the rod and the shaft. Both of them may be circular, they may be rectangular, but bar or rod is different than shaft. So this is the rod, or this is also called as the bar. And if you have a force, this is the force F, and this is the area A. As you can see that this force is perpendicular to area. That's why this is called as the normal stress. And normal stress is denoted by symbol sigma F divided by A. The unit is Newton per meter square or Newton per millimeter square. That is also called as pascals. Now, please understand what would happen to this rod under this load. This rod will get extended because the load is pulling it. So it is stretching it. So this stress is called as tensile stress. Now the next question is, what happens when I reverse the direction? So this is F, and please, this is again the normal stress, okay? But here the load is compressing the rod. So this is compressive. So the key takeaway here is, in both the cases, you have the load that is perpendicular to area. In one case, load is stretching. That's why you have tensile stress that is denoted as sigma T. In second case, what you have is sigma C, which is F divided by A. Again, Newton divided by meter square, which is equal to Pascals. Now the next stress is shear. The only difference between normal and shear is area is area is parallel. So in shear, load is parallel to area. Now what does that mean? So for that, let me give you a simple example. Again, we have this rod, but the load is applied something like this. So this is load F, this is area A. And this is denoted as tau, which is P divided by A. Now, here is the key difference between the normal and shear loading. Normal loading will cause either the extension or the compression. So for an example, if you have an element is a very small teeny tiny piece that is loaded, okay? So think about it like you have this small teeny tiny piece here, and this is when magnified, you would observe that this element would either stretch or would compress. But now I want you to visualize what happens to the element here. And the way it works is basically this element gets deformed and it's basically not extended or compressed, but element which was rectangular, now the angle got changed. So initially both the edges were at 90 degrees. Because of the loading, it changed. So now I want to show you sort of pictorial view, front view, wherein because of the shear stress, this element got deformed, something like this. Now what happens because of the normal stress is you have change in the length. So I'm going to write this down here. So you have something called as delta L. Delta L is final length minus initial length. And this delta L could be positive or it could be negative. So you can think about when the loading is tensile, the delta L would be positive. When the loading is compressive, delta L is negative. And this gives us something called as strain. So what is strain? Strain is change in the length divided by initial length. In the case of tensile loading, the strain is positive. In the case of compressive loading, the strain is negative. So tensile loading, strain positive, compressive loading, strain negative. Now this would be a perfect time to talk about something called as shear strain. Shear strain is given as gamma. What is the shear strain? Shear strain is nothing but the difference between the angles. So initially, as you can see, that this element was 90 degrees, though both sides were perpendicular. After the loading, the angle changed, and this change in the angle, so change in the angle is the shear strain. Now, this would be a perfect time for me to just tell you, please understand that the stresses that you have probably studied in mechanics of material or engineering design, they are manifestations of these two preliminary stresses. And it may not be clear. So for example, if you look at, we are going to discuss that, when you look at bending, the stresses that are induced in bending are normal stresses. The stresses that are induced in twisting or torsion are shear stresses. What happens if you have a combined action of normal stress and shear stress? This point extremely important. So what happens when you have a combined action of normal stress and shear stress? Think about it. Normal stress is normal, perpendicular to the area. Shear stress is parallel to the area. Recognize that it's like you have a force in x-axis and you have a force in the y-axis. If when you have these two forces acting perpendicular to each other, what you get? You get a resultant. That resultant force is principal stress. Remember the principal stress that you talked about? So what is the principal stress? Simply put, principal stress comes into the picture when you have the normal forces or normal stresses and shear stresses acting simultaneously. Now, so what happens when you have, what does it mean for maximum shear stress? Maximum shear stress comes in the picture again when you have normal stresses and shear stresses acting together. So remember this very, very carefully. Principal stresses, maximum shear stresses, those are sort of the resultant when normal stresses and shear stresses act together. Very rarely in practice, you're going to see a case where only normal stress exists, only shear stress exists. You will almost always, you will see sort of a combined action of these two different stresses. I know, unfortunately, you have not done any experiments in the mechanics of material or for that matter in engineering design, but here is a thought exercise that I want you to think about. Imagine I give you a rubber band or I give you a very elastic material, and then you grab on both sides and start pulling it. What would happen? Initially, that material or that band would stretch. You let the force go, band would go back to its original position. What happened there? There was elastic deformation, which means you removed the load, the band or the material went back to its initial position or initial state. It was elastic deformation, which means pull, let go, goes back. Now you apply the load further, what happens? That band or that material undergoes plastic deformation, which means after you, even if you let the load go, it doesn't go back to its original size. It stays deformed, may not be as deformed as it was when you apply the load, but it's deformed. So it doesn't go back to its initial position. What happens next? You pull that further, you would observe in metals like steel or mild steel, they will start, the material starts giving up, which means the material starts yielding. Material no longer holds those atomic bonds together. Material starts giving up. And then for the same force, material would continue to deform. And that again, what happens because of that deformation, the length increases, the area decreases. So you would have localized high stresses. And these high stresses, if they exceed the inherent property of the material to stay together, the material would break apart. That is exactly happens in something called as the stress strain diagram for steel. And I'm pretty sure that you have seen the stress strain diagram in practice. I mean, at least in the textbook. It is really unfortunate. We have 5 tensile testing machines on this campus. And tensile testing and breaking materials was one of the fun things when I was teaching mechanics of material. And you will notice these failure theories that you studied. I don't know if you, I think you studied like von Mises or maximum principal stress theory, maximum shear stress theory. Where do those came from? Those are theories, right? What are theories? You observe something experimentally and try to come up with a scientific explanation like, hey, this might have happened because of that we are seeing this. Those theories came because of the experiments. So for an example, if you have an aluminum rod or if you have an aluminum dog bone specimen, you put that in the tensile testing machine and you break it slowly, you would observe, interestingly, all aluminums fail at 45 degrees. Why? Why would aluminum fail at 45 degrees? Why not 60 degrees? Why not 70 degrees? Why not 80 degrees? And why does it fail at 45 degrees only when the load is applied slowly, not quickly?
Elasticity.
So let me tell you, when the loads are applied quickly, elasticity is gone out of window. Material does not have time to react. Imagine somebody is not coming to you and hitting you. If you're not prepared, you'll be taken by surprise, right? That's exactly what happens. So all the stuff that you have studied, it's for slow quasi-static loading. Unfortunately, life is not slow. Life is not quasi-static. In the internal combustion engine, the engine is running at, if you think about the engine in your car, idling at 800 RPM. 800 RPM, if you think about it, it's a 4-stroke engine, which means 400 cycles. I mean, if you see, 800 or 1000, about 1000 RPM, divide that by 60, and you will find out that the engine is performing those many revolutions, which means, just to give you an idea, the fuel has microsecond to ignite, burn, create power, and apply that force onto piston. What I'm trying to say here is, it's not quasi-static loading. It's very fast. Still, we can design those. So what we do is, again, you must have studied the design for fatigue loads, design for repeating loads, Soderberg line, Goodman line, right? Remember those lines? Time to rethink about this. Okay, so the point here is, so think about what is the practical application of that? Why do we need to use those guidelines? Why do I need to use those lines? Where do those lines came from? All the theories that you have studied, von Mises, maximum shear stress theory, maximum principal stress theory, those came from experiments. So here is the experiment told us that aluminum fails at 45 degrees. What is the logic? If something has failed, which means some stress exceeded its built-in, the material's built-in capacity or built-in strength, if I use the right word. Now, what happens at 45 degrees? That plane is the weakest plane for aluminum. What do I mean by weakest plane? Now, I want to give you a simple example. Imagine you are trying to cut an apple. Okay. What is easier, cutting apple like this or cutting apple like that? Assuming you are using the same knife. Clearly, cutting apple at 90 degrees, it's quicker and easier because apple as a material is the weakest in that plane. Same thing happens to aluminum, but because how the grain, actually I give an example, because how the material is organized or how the bonds are structured, that is the plane where aluminum is the weakest. Same thing happens with the wood. We have seen the wood is stronger in one direction and weaker along the grains. That is because how the material is, and that gave rise to the failure theories. One Mises theory, okay, principal stress theory. Where do this came from? So it came from like when the combined action of normal stress and shear stress. This is the logic. When the combined action of normal stress and shear stress exceeded the resultant normal stress that the material can withstand, the material failed. And that is the layman's explanation for maximum principal stress theory. Textbook doesn't give it that way, but let me tell you what that means. You have normal stress, you have shear stress. These two shear stresses, or these two stresses, they fight with each other. And because of that, what they do is they make each other more mad. Think about it. So this combined action, the resultant, basically increases the total normal stress in the normal direction. Also, it increases the total shear stress in the shear direction. And if that total normal stress exceeds the inherent capacity of the material to withstand that level of normal stress, material fails in that particular mode. So basically, that is maximum principal stress theory. Some materials fail in the maximum principal stress direction. For example, brass. For example, steel. Now, what happens with the shear? In shear, same thing. The overall magnitude of shear stress got increased because of the action of the normal stress, and the material couldn't take it. So material snap in the shear direction. And that is the justification, or that is how the maximum shear stress theory came into existence. So what is the takeaway here? Takeaway here is, depending upon the material that you choose, you would use appropriate theory. For example, if you are going to use steel, you would find out one Mises stress in your finite element analysis. If you are going to use some exotic material, which shows the characteristics of a maximum shear stress theory, then you will find out the maximum shear stress using your finite element analysis. For composites, it's a completely different ballgame altogether, because those properties are direction dependent. But you can do that. You can use the same principles, and then you can actually do that. Okay. So this would be a perfect time for me to draw stress strain diagram for mild steel. So if you look at a mild steel component, and I'm sure you have done this. So you have stress on y-axis, you have strain on x-axis. So what you do is you have this component. Usually it's a dog bone type of specimen. And when I was in grad school, doing experiment like this was fun. But what we used to do is we had to use something called an extensometer, where it's a gauge that you attach, and basically you see the deflection of the gauge. But now what you can do is you can do something like displacement, or you can do stress strain curve using iPhone or iPad. You can actually set up the optical markers and then it will tell you, just like it tells you the height of the person, it will change you it will give you the deflection that is changing with respect to time. So what you do is you mark 2 points. This is called as the gauge length or initial length. And then what you do is you start applying load. You measure the initial area. So initial area AI is known. And then what you do is you create a table. You have load and you have change in the length. And then I'm just going a little bit going quickly because you have done this. So what you do is you will have P1, P2, P3, etc., etc. You would have delta L1, delta L2, delta L3, etc. The important point is to find stress, you will divide all the P's by initial areas. You will divide all the P's by all the initial areas, and you divide L's by the initial length, or something called as the gauge length. And then you'll plot this and you'll notice this type of behavior. Now, it is interesting to observe this type of behavior is seen in the mild steel under 2 specific conditions. First condition is that division is always by initial area and initial length. If you divide that by the instantaneous area or instantaneous length, you are not going to get a curve like this. So please understand, all the stresses are calculated with initial area, but recognize as you are pulling, at some point that area start decreasing, but still you are using the initial area. Length, as the length is increasing, please note the length for the previous step was different than the initial length, but still you are using the initial length. And second thing is the loading is very slow. This is called as engineering stress strain curve. Underline engineering. This is not a true stress strain curve. If you are interested in a true stress strain curve, you're going to see something like this. This is engineering stress strain curve. This is called as the true stress strain curve. Now, depending upon what you're interested in, you will observe that this engineering stress strain curve has region for elastic deformation. This is elastic region. And then you have plastic deformation. Then what you have is you have something called as the upper yield point, lower yield point. You have the failure, the maximum stress, and you have the failure stress. So these are the important points. So as designer, as engineers, we do not want to go in plastic region. We always want to be in the elastic region. But recognize, in elastic region, we don't want to be at the boundary. You don't want to sit in a car, that car buckles. It's safe, it has not failed, but buckled. You will not feel comfortable riding that car. So basically what we do is, we try to be at level which is somewhere over here. And the difference, the ratio of this, so sigma design and sigma yield is called as factor of safety. So sigma yield by sigma design is called as factor of safety. And we need factor of safety because we don't know for sure that if the material is homogeneous or if it has some impurities, or if it may have something that we don't know. So to account for all the assumptions and the mistakes that we make, we actually add factor of safety. Okay, I'm gonna stop here and I will continue this discussion in